Well, hello again. All right, so hopefully we've got this down to a science. Going to try and be efficient. Hopefully you guys know about how to speed up YouTube videos. Sometimes I get a little rambly or want to make sure that I'm giving every detail, but you might not need every detail every time. So feel free to skip around. Will not be offended. Okay, so now we're looking at units 2 and 9. This is review for two variable data, working with it, and then a little bit on that inference for slopes. Again, it's not a huge component, so we're going to touch on it, but not worry about it too much. Okay, first up, describe for a scatter plot. So since this is two variable data, if you would make it a scatter plot, you're going to describe using strength, uh, form, and direction. And always in context, 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 context. So, strength can be weak to strong, and it can be moderately strong. It can be, a clear relationship without being terribly strong. Like you can qualify that. Form is going to be linear or nonlinear. For our purposes, I just want you to describe it as linear or nonlinear. Don't worry if you can see that it's exponential or whatever. Just is it linear or nonlinear? And then direction. That is going to be positive or negative. Kind of along the same lines as slope. However, I don't actually want you to use the word slope in your description because it's not correct to use it if it's not a linear relationship. So if it's going like that, it's nonlinear with a negative association. That's all we say. It's a negative association, not with a negative slope, because that's not quite right. All right, good. Next, is a linear model appropriate? How to know? So, from the scatter plot, you should see that it's kind of a line. From the residuals, if you run linear regression or you're looking at a plot of the residuals, you should see no apparent pattern. So it's really, really important before you decide is a linear model appropriate. Are you looking at the scatter plot or are you looking at the residuals? Because you want to see very different things. Okay, good. Next up, write the LSRL, least squares regression line equation given the regression output. So the context of this problem, I just simplified it. Predict the final exam score from hours spent studying. Okay, so first up, if we want to use X and Y, let's say X is our number of hours studied, which means Y is our final exam score. Remember, if you use variables, you must define them. Then we're going to say Y hat, because our regression equation is always a prediction. So Y hat is equal to, and then we're going to use these values for our regression equation. We'll come back to the other ones in a minute. So our constant is our y-intercept, because that doesn't have an x with it. Plus, because the coefficient on the study hours is positive, 2.697x. So that is our least squares regression equation given the regression output. And again, this comes from here. And the constant without the x comes from here. The other way you could write this, if you didn't want to define variables, or you might even see this, is we could say the exam score. And again, we can just put that hat over exam score to show that it's a predicted value, is 6.3, nope, 62.328 plus 2.697 times study hours. And so again, same numbers, same exact equation, same scenario, but instead of using variables, I just threw the words in there. Both are totally fine. Okay, onward. Interpreting the slope. Remember, this is a sentence stem. You should memorize it. Many of you have, many of you haven't. The decision is yours at this point. So, to interpret the slope, for each additional hour of studying, the final exam score is predicted to increase by about 2.697. It is incredibly important, again, is predicted by about, and it's for each additional hour of studying. So whatever this is. And then whatever this is, whatever the output is, that's what's predicted to go up or down by the slope. All right. Cool. Not going to belabor that point. Sorry. Then interpreting the y-intercept. If the number of hours spent studying is 0, so the y-intercept always happens when x is 0. The predicted, this is still a predicted value, not predicated, predicted exam score is 62.328. And that actually does make sense in context, so that's nice. Sometimes it'll make sense in context, sometimes it won't. Okay, y-intercept. Slope. Now, we didn't do a ton with this. That's okay. Figured it's nice to have. So the slope, remember y hat is equal to a plus bx. And so that means b is our slope. We can get that, we can calculate that by saying b is equal to r, so the correlation coefficient, times the standard deviation of y over the standard deviation of x. If this seems brand new to you, that's okay, because it also means we haven't used it, right? It's not something I want you to stress about. It's not a good use of your time. If you're feeling great about everything, yes, learn this, right? There's one more multiple choice question, maybe. But if there are bigger fish to fry, go fry those other fish first. Like residuals. Everyone needs to know how to find a residual. Just as a reminder of what a residual even is. Nope, not an image. Come here. So, a residual is the difference between the actual amount and the predicted amount. The actual amount and the amount predicted by the LSRL. That's a nicer way of saying it. And so to calculate that, you're going to do y minus y hat, and that's going to equal your residual. So it's actual minus predicted, and that is your residual. Now, as a note, if the residual is positive, I'm going to move this. Maybe. Okay, so if residual is positive, LSRL was an underestimate, right? What we predicted was less than what we actually ended up with. Conversely, if the residual is negative, then the least squares regression line was an overestimate, right? We ended up lower than what we would have predicted. Cool. Now, to find a critical value, to find the T star, if you're going to make a confidence interval, this is when you do inverse T. We're going to say T star is equal to inverse T. And then for your area, you're going to do, in parentheses, 1 minus this confidence level all over 2. And then your degrees of freedom is going to be your sample size minus 2. Remember that this will always be negative. But that doesn't matter because it gets washed out. Washed out by the plus or minus in the confidence interval formula, right? Something plus or minus the T star. So if it's negative, we'd just be subtracting a negative, which turns into a plus, and then we're adding that negative anyway, which turns into a minus. So this just means it always gets you to the right value. Just ignore the negative sign on it. Okay? Yeah. Next, construct a T-interval for the slope of an LSRL given a regression output. Okay, so we're going to use this regression output up here. And actually, I'm just going to screenshot that and bring that regression output down to us. You can flip back and forth. You can copy the values down. Whatever makes you happy. Except not doing it. Okay. So here's our regression output again. And we're going to construct a T-interval for the slope. It does not give us a sample size. So right now, it would give you a sample size in any reasonable situation. I'm just going to say to assume n equals 20. And let's just assume also that we want a 94% confidence interval. Everything in that purple right there, I'm completely making up out of thin air. It's just so that we can move forward. In any question, you're going to have that information. So make sure you know what the sample size is and what the confidence level is. Okay, so T-interval for slope. Our interval is going to be the slope we got plus or minus the t star times the standard error. The actual slope we got here was 2.697 plus or minus. The standard error, what color haven't I used yet? I'll use gray. The standard error is this 0.745. It's the standard error for the slope. What we don't have yet is the t star, so I'm going to calculate that in a second, but I'll pop my standard error in because it's already given to me. So that's my standard error, and this was my slope from before. So to get our t star, I'm going to use inverse t. I'm going to say that the area is 1 minus 0.94 divided by 2, and that the degrees of freedom is 20 minus 2, sample size minus 2. When I pop all that into my calculator, into inverse t, 1 minus 0.94 divided by 2, degrees of freedom is 18. We get a t star of, again, I'm going to just ignore the negative sign, 2.007. So that's what's going to go right here. And then to actually construct the interval, I have to do the calculation. So 2.697 plus 2.007 times 0.745. I could have done the minus first, actually, to get the low end first. Always do your intervals low to high. So on the low end, we're going to get 1.202. And on the high end, we got 4.192. So there's our interval. And then for interpreting it, it's the same we are blank percent confident as we always use for confidence intervals. But this time it's not about the value or a difference in value. It's about the actual slope. So we are 94% confident that the interval from 1.202 to 4.192 contains the actual slope of the relationship between hours studied and final exam score. So instead of being what the score is, this interval is about the slope of the relationship. Okay. Cool. So then, to do a t-test for slope, you really are unlikely to have to do this. More importantly, there's our p-values. We could do TCDF with this, we could do TCDF with that 3.62. But we also know that we have our p-value already here of 0.005. So I'm just going to write the conclusion. So we're going to have two sentences, and we're going to start with because. Because our p value of 0.005, again, that's coming from up in that top right with the study hours p-value, is less than any reasonable significance level. We would reject the null that the slope is 0. So in these tests, the null is always going to be that the slope is 0. Okay, so there's sentence 1. And then here is sentence 2. we have convincing evidence that there is a positive relationship. And I'm saying positive because the interval contained only positive values. Our slope was positive. Like, it can't be positive or negative because then zero is a possibility. So that there's a positive relationship between the number of hours studied and uh, and the final exam score. I was thinking, like, do we even want to say that it's positive? But sure, let's be bold. If you wanted to be conservative, you could just say that there is a relationship at all. That would be probably the true alternative, would be that it's not equal to zero. Okay, cool. Units 2 and 9, notes. Good. All right.